Hi everybody. I've just been watching a couple of YouTube videos about hidden figures, and one of the clips from the film I saw, there was mention of the Euler method, and I thought I'd program that in COBOL so you could see what that looks like in COBOL. The basic idea of the Euler method is it's a way of solving differential equations. It's a numerical method. And the basic idea is that if you have a numerical equation which you can't solve analytically, so with some you can, so you say for example dy by dx is equal to y, then you can solve this one analytically and you get the value of this means that y is equal to a times e to the power of x. If I do this, let's write it like that, is the analytical solution for this differential equation. But there are lots of differential equations where you have a function of x and y here which really don't let themselves be solved analytically, but you can always find a numerical way to do this by saying, well, here I have a function which gives me a value of a slope at a certain point. So if I am at this particular point, if I say my value of x is 1, my value of y is 1, then I have the value of the slope. And then if I say, well, what's the value of y going to be at x plus delta x? Well, you say it's going to be the value of y at x plus the slope times delta x. And this is the basic intuition, and you gradually build your path using this function. So I thought I'd try this in COBOL so you can see what this looks like. Multiplication, division, and then I'll try plotting it with something like GNU plot, and I'll try with a simple function to begin with, like the exponential function, so we can see if that works or not. Is proc01, I've called it environment division. Let's save our values to somewhere. Input, output, section, file, control, select, out, file, assign to, let's just call it values.dat. Organization is line sequential. Okay, then we need our data division, and we need a file section, and let's fd out file 01 record, and let's have a 05 which is x out, which is going to be a pick of, let's make it assigned 5 with 2 after the decimal point. We can change this later to something which we think may be better. Y out, big S9, 5, 2 after the decimal point. Okay, and then we need a working storage section. And let's say we start with a certain x0. Let's call them an x, which is going to be a usage is computational 2. Let's have a 01y, usage is computational 2. Now we want a slope, which I'm going to call m for traditional reasons, is computational 2. What else do we want? We want a delta x, just going to call it dx. What else do we need? Probably how often do we want to repeat this? So let's have an x0, an x min, and x max as well. Let's have an x min and x max, that sounds good. X min usage is computational 2, and 01 x max usage is computational 2. Okay, this way be enough. So let's start 100 main. Let's open the out file for output, and the end is going to be, of course, close out file and go back. Okay, let's display, enter. Let's make it, or let's not bother with entering the values. Let's just say move 0 to x, move 1 to y. So we're going to be solving it for the case of this coefficient a being 1. So we're going to start at x0 as y is 1. Move what to dx? Let's say move 0.1 to dx to start with. We don't need an x min because we're starting explicitly. And let's have, don't really need an x max. Let's have a num steps. Pick x, sorry, pick 9, 4. Okay, like that. And let's move. Actually, we just need a step num, don't we? No, let's have just a global variable. And 0, 1. Let's have an I. Pick 9, 4. So let's perform our calculation. Varying I from 1 by 1 until I is greater than num steps. And let's set a value to num steps. Move, let's say 20 to num steps. Okay, so let's have a look at our 200 calculation. What we need to do is we need to get a value of a slope. We need to modify. Oh, no, we don't get a value of a slope, do we? I see the problem. Let's move 0 to m. So we have to be careful that we don't start by adding something. We want the first value saved to be x and y. So let's do that. So let's move x to x out. Move y to y out, right, out, record, and let's do some calculation now. Let's have a perform calculate slope. Let's make this 300. Okay, and let's move here. 300 calculate slope. M, let's make a compute. M is equal to, well, if we're just using the exponential, the m is just equal to the y coordinate, isn't it? So move y to m. That's it. That's the slope. Okie dokie. So let's recalculate the y here. Compute y equals, which way around do you want to do this? Let's do this here. X add dx to x giving x, and here we have to compute because it's more complicated. Y equals y plus m times dx. Okay, this may be enough. Let's see what this does. I probably got something wrong. Let's see. ls, okay. Siemens x prog 01 and prog 01. What have I done wrong? Dot kann nicht auf s folgen. Okay, yeah, that's true. I'm mixing two different things here. I'm mixing one notation which is for internal working with numbers and one notation which is for formatting for external use. So let's turn this into a minus. Let's see if this now works. ls. We have a values.dat. Let's see what's in it. Okay. This looks okay. Doesn't look bad. And I have this GNU plot. I can start it here and plot values.dat. Let's see what it looks like. Doesn't look bad, does it? Seems to have worked. Let's add plot values.dat and add x of x. I think this is how you do it. Yes, that's not bad. It's not perfect, but it's not bad. Let's increase the accuracy a bit by putting, let's say, 0.01 to dx and putting 200 to num steps. Let's run this again and let's plot this again. And now, oh, that's really very good. That's suspiciously good. Can I zoom in somehow? I'm not sure how. Ah, it is too good, isn't it? And it has a strange jump here. So something's gone wrong. Let's go back down to a smaller number of steps. Move 0.5, 4, and no, this window. What are we looking at here? How do I zoom out? I don't know how to do this. Hello, how do I do this? Replot, no. Show grid, well that doesn't really help, does it? How do I zoom out? Oh, here. That doesn't seem to do anything. Previous zoom, next zoom, auto scale. Ah, okay, got it. Oh, that looks better. It's much further below now. You can see how it gets to this value here. It's 0.5, 1.5. That makes sense. And then it goes to 2.25. Yes, this is correct, isn't it? Because it starts by saying that the slope is 1. And I go up with slope 1 for 0.5, which gets me to 1.5. Then the new slope is 1.5. And I go up with slope 1.5 to 1, which gives me 2.25, etc. This looks okay. Okay, let's try to do something else. What we have here is we are mixing lots of different things in one file. To start with, we have this calculation for calculate slope, which is, yeah, we have to write our function here explicitly. So this is our differential function here. This is dy by dx equals y. This is what we're doing here with this calculate slope. One thing we could do is we could move this to an external file and then call it, which may be interesting. Let's try to do that. Let's call it exp.cob or expfunc.cob just to make sure I don't clobber function name. Okay. Identification division. Program ID expfunc. Now we need a data division. And we need a working storage section. That's actually, we don't really need a working storage section, we just need a linkage section, don't we? In the linkage section we have a 01x, which is a usage is computational 2, and we need a 01y, usage is computational 2. We need a 01m, usage is computational 2, or comp2 you can see as well. We need a procedure, division, using x, y, m, and all we do here is move y to m, and then we go back. So that's our exponential function. Wrong button. Let's go back over here and let's use it. Let's call exp_func using x, y, m. Okay. So what we're doing now is we've taken the function which we're actually trying to solve numerically, and we put it into another file. Okay, let's see if this works or if I've got something wrong. Let's do a cobc exp_func.cob. Looks okay. Cobx. Let's remove data, was it? No, values.data, just to make sure. And let's run this. Calculate slope is not defined. Paragraph calculation. Oh yes, that's got to go. We've got this values.dat. Let's see if that still works. Yes, it does. So we get the same values out in the end of the day. Perfect. Okay. The point of this, one of the points of this is, yes, we've moved this functionality into another file which we can then use, but one thing we can also do is we can choose which functionality we want to actually perform. So let's have here a 01 func name. Let's call it func name. Here's a pick x20 value exp_func. And we can call func name. Let's remove values.dat and let's call it again. Let's go to GNU plot. We can see it. It's done the same thing. This is the point of this. Is it allows us to use some sort of polymorphism, for lack of a better term. You can choose which function to call here. This is dynamic linking. This is why GNU COBOL does dynamic linking. And you can decide to use a different function. It doesn't have to be the exponential function here, which you are solving numerically. You could solve a different function numerically. One thing we could also do is we could, instead of solving this function numerically, instead of just having this one level here, of having this idea, we have here the idea of doing performing the Euler method, That's what we have defined here in this calculation. This bit here is the Euler method. And we could export that to another function as well, to another file as well. And the Euler method could decide to call the exp_func. And we could save all the values the Euler method generates in an array which we pass to it. So what we'd be writing here is we'd have a call Euler, or call whatever you want to call it, linear numerical method, we could call it, using xmin, xmax, num steps, that sort of thing, x0, y0, and an array where the answers are to be put. We could do it like that as well. So let's see what that would look like. Let's make an Euler.cob as well. So we have an identification, division, program ID, Euler. We have a data division. We don't need an environment division. We have a working storage section. We'll need this. And we have a linkage section. Then we have our procedure division. So what do we need in the linkage section? Well, we need an x start or an x0 if we want, which can be a usage is computational 2. I didn't tell you what a computational 2 is. That's a 64-bit float. This is what it happens to be called. I think in Java it's called a double, isn't it? It's according to IEEE 758, the definition for how these 32 and 64-bit floats work. They're, every chip nowadays has circuitry just to deal with these float numbers. Let's make a Y0, which is usage is computational 2. If we want to send the values, we also need a result array 05 results occurs, let's say 100 times, indexed by I, and let's have a 10. X is usage is computational 2. Well, if we do it like this, we don't need an X0 and a Y0, do we? Or do we need an X0 and a Y0? We could just save them in the X and Y here. Let's do it explicitly like this, just to make sure. And let's have a 0, 1 num steps. Pick 9999, and let's have a 0, 1 delta X, usage is computational 2, and we also need, of course, the function we want to call, which is going to be 0, 1 func name, we're going to call it, which is probably not the best name, we need to find a better name for it, but whatever, x20. Okay, so it's procedure division using x0, y0, num steps, delta x, result array, func name. There's a lot going on here. And theoretically all we do is we start by moving x0, no, we perform a calculation. Perform 200 calculation varying I from, or we can cheat, can't we? We can say 2 by 1 until I is greater than num steps. Okay, then we just do a go back. That's it. 200 calculation. And what do we do here? Let's start here by move x0 to xi. Let's start by move 1 to I. No, let's just do it with x1 here, why not? And move y0 to y1. Calculation, okay. What do we do here? Let's get the slope. Get that later. Move. Let's do this into calculation. We need an m for the slope, don't we? 0, 1, m. Usage is computational 2. Then we can say move this here. Call func name using x0, so yeah, y0 m. Then we get the initial slope. Then we say y I, calculate, you need to compute here, y I is equal to y I minus 1 plus dx, so I plus dx times slope times m. Okay, and we need a x I is equal to, let's just do an add, dx to x I minus 1 giving xi. Okay, and then we calculate a new slope, I suppose. Call func name using x I y I m. Okay, let's see if this now works. Hang on, we have got to do a lot more work until we can check this. We have to add it in here as well. So we need to have everything here for the working storage section. So we need a result array. We can just copy the same thing, can't we? We're not interested in an m. We can, here we have a dx as well. We need that. Have num steps. We don't need an I. We have a func name. That sounds good. Okie dokie. Let's have an x0 and a y0. Okay, and now we can probably call it, can't we? Open up a file, didn't do that yet. Let's get rid of all this. Okay, so now we have our Euler method, so numerical method. Euler, okay, so we call numerical method, because there are all sorts of ways you could be doing this. You don't have to use Euler. Using, what do we do? We use an x0, y0, num steps, dx, result, array, func, name. Oh, it's too much. Ooh, I don't know what it, to see if it likes that or not. I've never tried to spread parameters over 2 lines before. Okay, so we need to initialize these. Move 0 to x0, move 1 to y0, move, well, we're doing it 100 times, aren't we? Let's say move 10 to num steps. What did we have? We had 4 in num steps, didn't we? Let's move 4 to num steps. Move 0.5 to dx. Okay, that should do it. Call numerical method, then we can save it, can't we? Wasn't correct. Perform 200 save array. Okay, cool. All this disappears. Wrong button. 200 save array. What do we need to do first? Have we indexed this? I've got an index by E. Okay, so perform varying E from 1 by 1 until E greater than num steps. Move x e to x out, move y e to y out, write out record, end perform. Okay, let's see if any of this works. I've probably got a lot wrong here. Let's start with compiling Euler. Yep, it doesn't like that, does it? What isn't it like? It goes along line 13. Result array. Okay, there's a dot missing. 29. Yep, it won't like that. It needs spaces. Okay, it compiled. This is a good sign. Let's try running that as well. Okay, we have stuff. Let's remove values, make sure it works. And let's plot it. What do we get out? Yep, it's the same thing, isn't it? 1.5, 2.25, etc. Let's change the number of steps to 100. It's 100 times. Let's go to 80 and 0.03 or something. Nope. What's it look like now? Yep. Cool. I'm quite pleased that this worked. I don't do this very often, so I'm pleased that it worked. So here you can see what we've done here is we've extracted the idea of the numerical method to its own function. And we're saying a numerical method has to have this sort of interface. 0, y0, num steps, etc. What's the time doing? How long is this already? Where's the time? 32 minutes. I think COBOL will catch you if you do something wrong here. Let's see what it does. What happens if I miss out an argument here? What does COBOL do? Yes, it doesn't like that. What happens if I mix up arguments? Oh. Yep, it doesn't like that either. Okay, so it's a little bit of type safety going on here, and now it's happy again. But the error message is quite strange. What happens if I've already done a fair amount of work by the time I make a mistake? When does this explode? Display now here. Is it a compile time? I doubt it is, but let's make sure it's not a compile time. Get rid of that. Now here. So this explodes at runtime, and the compiler can't see an error, which makes sense. Why should the compiler check it? This is one of the examples, one of the advantages of using a language with type safety, and where you can analyze the code better than what Emacs can do here. For example, I got my JetBrains here, and I just started something called numerical methods here in Java. And if I create a new Java class here, add dot, let's call it numerical as a class, and it's sorry, class names are capital, aren't they? Vector. Class names are capital in Java. Let's have a public static void main. Let's make a new Java class. Let's have a Euler here, an Euler, and let's have a Java class exp as well. And exp has a function in it which gives a double back, and this is get slope is the name of the function, and it takes a double of x and a double of y, and all it does is return y. These should be written small, shouldn't they? Because we're now in Java land, not in COBOL land. Okay, and the Euler function, what it will do is it will say we need a list of double let's make a list of point. We need a point class, which I will define. Let's make a point class. Oh, we can make an internal class, can't we? Public static class point, and we need a public final double x and a public final double y, and then we can have a public point of a double x and a double y, and we can say this dot x equals this dot y. So now we have, sorry, this dot x is slash x, and this dot y is equal to y, etc. So we have a list of points. We can have that. Java auth. I don't want Java util. I want for a list, don't I? Get points. We need some values here. What am I doing here? Yes, this is just totally wrong, isn't it? This should be small. I'm sorry, I'm not in Java mood at the moment. I'm going to make a lot of mistakes and correct them all the time. And what we could do here is we could introduce the idea of a differentiable function or something, or of a differential equation. So let's have a new Java class, an interface, which I'm going to call differential equation. And differential equation has one method, which is a double get slope, which takes a double of x and a double of y. And then in Euler, I can say, give me a differential equation here, dE, or differential equation, give me an x0, double x, x start x. Let's give a point start differential equation. We need a num steps, and we need a double delta x, and then we can calculate our particular method here. And the interesting thing is that we've now defined the idea of differential equation. In Java, you also have to explicitly say that this implements differential equation, don't you? Okay, and it doesn't at the moment. What am I doing wrong? Oh, it should be public. Okay. And Euler gives back a list of points. You'd make a list. Oh, I can't type. Points is equal to new array list, etc. And you'd say for int e is equal to 0 equals 0. Sorry, wrong language. E is less than steps e plus plus. So that should be like this. You can say points dot add. Let's have an x double y. Add a new point x y. Let's move x start. Actually, we can just add start, can't we, to begin with? Point.add start. Then we need a new point, don't we? Here, which is we get slope. Well, you need to fix the slope somewhere. Double m. Oh, I've called it slope. Slope is equal to dE differential equation dot get slope from start dot x start dot y. I could just use a point class there as well, add a new point, and what we do here, we can just add a difference to it, new point. So slash 1 and steps. Let's get points. Let's use an X and a Y here, etc. You can see what you can do. The main important thing is to see that we've now got this type safety of having a differential equation, which can be checked at compile time. And the same thing when we go up to the idea of having a numerical method, we can have the idea of Euler, have the idea of get points, we can save that in an interface. And this doesn't work that well in COBOL. It doesn't have the same amount of type safety. I may finish this off and put it online. Okay. Hope this was interesting to somebody. Hope to talk to you soon. Bye.